Good afternoon, everyone. Today we are in section 10.5. So far, we've spent all of our time studying positive term series only. We've developed tests for those, ratio test, root test, blah, 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 blah. So today we move into series that have negative terms in them also. So the first type of series, negative, so ultimately what happens is the negative terms impact things. They change things. If one's positive, one's negative, you're adding those together, it's getting closer to zero in a different way than if you're adding like 2 plus 1 plus 1/2 plus 1/4, getting smaller. The negatives actually change things a little bit. So there's basically two types of series with negative terms. The first one is just an alternating series. It's anything that looks like this. So what we're going to do is we're going to take our series, so anything we've done before. If you think about any series we've ever had before, you could just put any one in a sub n, and then you throw in this little negative 1 to the n minus 1. That basically means that the term's alternating from positive to negative. It doesn't matter which one's first. It could be negative 1 to the n, or n plus 1, or n minus 1. It just means it's alternating. So you could take any series we've done before, and you'll see a couple of examples. Actually, let me pop this one up here as an example. So like we've studied this one before. We could do a test on that one. If it didn't have the negative in it, but the negative in it changes the test. Okay. So the first test, so this is a new test right now. This is actually called the alternating series test. It's actually much easier. It's kind of cool, actually, much easier than with just positive. So in this particular one, we would have to do some sort of test, probably a limit comparison test if the negative wasn't there, right? Pretend for a second that that was not there. We would just probably do a limit comparison test. We would compare it to 1 over n. I'm just going to do that quick out loud. And we would get that it diverges, right? But the alternating series changes that, and it actually makes it easier to test. So here's how it works. All you have to do is meet two conditions, and it's really just one condition because the first condition's kind of a given. So first things first, the first thing that has to happen is the terms must be getting smaller. Forget about the negative part of them. A sub k must be greater than or equal to a sub k plus 1. So in other words, the k plus first term is less than the kth term or equal to. They're getting smaller or they're not increasing. That's kind of a given. You know, every problem we've ever done has to be getting smaller. If they get bigger, then they're just going to add up to infinity, right? So that's just we kind of leave that piece out of it when we do them. So the big one is this. It's kind of cool, actually. All you have to do is like an nth term test, in essence. Because of the alternating piece, all you have to do is check to see what the limit as n approaches infinity of the terms are, the a sub n. If it happens to be 0, then the series will converge. If it's not 0, then it will diverge. If it's not 0 in any other old test, it would diverge also. But remember, in the positive term ones, if the limit is 0, we weren't sure. Sometimes it was convergent, sometimes it wasn't. So it makes these problems a lot easier. So all you have to do when you're doing one here is just check this. We just go limit as n approaches infinity of 2n over 4n squared minus 3. This is just a limit of that higher power rule, higher power on the bottom, so it equals 0. Therefore, negative 1 to the n minus 1 times 2n over 4n squared minus 3 converges by the alternating series test. So really a pretty powerful test. The idea is, by the way, remember, this would not have converged without those negative 1 to the n minus 1. We would have had a test of the fact that they're both getting smaller, but one positive, one negative is pushing it towards its sum faster than it would have without the negative terms. Here's another example. This case, I'm just going to write up here because I don't want to take up the space below. I would just go limit as n approaches. So as soon as you see the alternating series, go boom, yeah, really cool, alternating series. All I got to do is find the limit of the terms. That's it. This is 1/2 or 2/4, right? Higher power rule, power is the same. 1/2 is not 0, therefore it diverges by the alternating series test. That's all there is to it if it's alternating. We're going to study this a little more in depth, so it's not quite that simple. If it's alternating, we could have series that have positive and negative terms, but that's not alternating, so we have to deal with that also. So here we go. Maybe our terms are not alternating. So what we do in this case is we look at something that's called absolute convergence. We ignore the negative 1 to the n minus 1 piece of it, and we just look at the positive terms. And then we're right back to where we were for the whole entire other chapter. Okay, so these are two little examples of what we can look at alternating. We could these are both alternating, so we could still do the alternating series test, but I want to point out two different things that can happen. So first, let's start with this right here in the pink. If a series is absolutely convergent, then it is convergent. So in other words, you could take a problem like this, -1, the first one here. We could do an alternating series test, I know that, but I'm just going to show you another way. I would do an alternating series test in this, but notice this converges, right? 1 over n squared converges. It's a p series. So by the absolute convergence, we know it absolutely convergence. It converges, -1 to the n minus 1. There's not a lot of series that have positive and negative terms in them that don't alternate. They're hard to make up. So we typically go back to the alternating series, but one thing you can do is that, okay? So you can just check the absolute convergence, but I would do an n-term test. So notice this one, all right? This one, the 1 over n diverges, right? So actually, I'm going to do something. Hang on 1 second. I'm just going to cover that up for just a second. So I want you to notice something. I'm just going to do this quickly to save some time. Both of these, try that again. Change the color so you can see it. If I did an alternating series test, both of these things in purple would converge because the limit as n approaches infinity of 1 over n squared is 0. The limit as n approaches infinity of 1 over n is 0. So they both converge by the alternating series test. But notice that, I'm going to change colors here. The positive part, that is the positive piece of that one, 1 over n squared, is a p series that converges. This one diverges. So if I did this same absolute value test down here, I'm going to change this to an n, 1 over n. 1 over n. This one diverges. So this tells me nothing because the absolute value diverges tells me nothing. So they're different, right? The 1 over n squared and the 1 over n are different. So we have this thing that's called conditional convergence. So let me do a little erasing here, and we'll just circle another one. So you kind of conditional convergence is any series where it converges, like this one, that whole thing in that circle that I'm circling 20 times here, that converges, right, by the alternating series test. However, if you look at the inside piece, the positive piece of it, it diverges. The absolute value diverges. That is called conditional convergence. So what's going to happen in the homework is you're going to get a new question, right? So before, excuse me, lost my voice here. Before we got asked the question, does this series converge or diverge? Now you're going to get asked the question, does this series absolutely converge, conditionally converge, or diverge? So we're going to have to check multiple things. Okay, we'll talk about some examples in a second. One of the things that's kind of cool is we can do a ratio test, again, absolute value. Okay, so you can do a ratio test. Actually, you know what? Before I do the ratio test, let me do this. Let's just do a quick little problem to walk you through. I'll come back to this problem in just a second. So we're going to go -1 to the n, or n minus 1, doesn't matter. We'll go n over n cubed plus 2, something like that. So the first thing I do, so the question was going to be absolutely converge, conditionally converge, or diverge. These are your three choices. So here's what you do. First things first is, notice it's an alternating series. So all I do with an alternating series is take the limit as n approaches 0, n approaches infinity, that equals 0. Therefore, the series itself converges by the alternating series test. Now, I need to check the absolute value part of it, which means just this, right? Just that. So it's like doing this series. I'm not going to write it all up. Well, actually, could I do a limit comparison test, right? Limit as n approaches infinity of n over n cubed plus 2 over 1 over n squared. That equals 1, which is greater than 0. This is a convergent p-series. So this converges. And it converges absolutely, right? Absolutely. This is absolute convergence. Okay. So my answer to this question would be absolute convergence. If I did this work here and this one diverged, then I would have what's called conditional convergence. You got to check both of them. What order do you check them in? It kind of depends. We'll talk more about that in class for sure. But what I do is I see the alternating series, do the alternating series test. If it diverges, by the way, you're done. Just say, boom, it diverges. I don't have to do anything else. However, if you get 0 and it converges, then you take the absolute value piece of it. If the absolute value piece of it converges, then you have absolute convergence. If it diverges, then you have conditional convergence. So here's just another example. Whoops, we'll do that one in a second. Here's just another example of the ratio test. It's kind of cool. The ratio test can solve you a lot of problems. If you do an absolute value ratio test and you get less than 1, just like the regular ratio test, it absolutely converges. If you get greater than 1, it diverges. But here's the catch. You don't have to check for conditional convergence. There will be no conditional convergence. Only if you do a ratio test. So if you can do a ratio test, which you can't always do, because remember, sometimes you get 1, which is bad. If you get a ratio test, you're good. So I'll just practice a little ratio test here. Limit as n approaches infinity of n plus 1 squared plus 4 over 2 to the n plus 1. I'm just going to multiply by the reciprocal right now to save a little time, but I would do divided by the nth term, which is 2 to the n over n squared plus 4. We do a little simplifying. I get a 2 on the bottom, and I got an n plus 1 squared plus 4 on the top, and n squared plus 4 on the bottom. So the higher power on the top is n squared. The higher power on the bottom is n squared. So that is 1/2, which is less than 1. It diverges. Now remember, I only check the absolute value piece of it. So if you go back to this problem, oops, I erased it. Sorry. Remember, in the old problems, if it absolutely diverged, you would have possibility of conditional convergence also. But in this case, we don't have to worry about conditional convergence. By the way, checking this limit can be a little tricky because it's not like a higher power rule. It's, oh, sorry. Oh my God, I messed all that up. Sorry, this converges. Yeah. So let me keep saying what I'm saying. Sorry, it converges. Less than 1 converges. You were all thinking, oh, Mr. McGurk lost it, right? Less than 1 converges, greater than 1 diverges. So let me backtrack. If it did diverge, you would not have to go back and check the limit. You would just say it diverges. If the ratio test works, there's no way you can get conditional convergence. We'll talk about that in class a little bit more. Last thing you can do with this, which is pretty cool, is you can actually now try to figure out what the sum might be. You notice we've been ignoring the whole time what the sum is. We're just saying, does it converge? Does it diverge? We've just been ignoring it. All right. So if we have an alternating series, it's pretty cool. Watch this. So let's just say, I'll just do this. 1 plus 1/2 minus 1/4. If we have an alternating series, if I add up those, let's say the first 3 terms, whatever I get, I can be guaranteed that the sum, whatever number I get, is within. So sum is within 1/8 of the actual sum. It's the farthest I can ever be off. The next term, in essence. Okay, if you notice what this theorem says right here, if you add up a partial sum, n terms, the partial sum will always be within, that should say a to the n plus 1. The next term, the n plus first term. If you add up the first n terms, the sum will be within the next term. And the reason for that is this: whatever these add up to, I'm going to add 1/8. But then I'm going to so let's say here's where I am, right? Sum and term. The next term I'm going to add is 1/8. So S sub n plus 1/8. But then the next term is going to subtract. So I'm going to go back this way. So I'm going to wind up in here. Okay. And then I'm going to go back this way. But I'm not going to go back as far as I already was. And then I'm going to go back this way. So this is the furthest away I'm ever going to be from the sum. So just the next term. So what you can do is take a series like this, 1 minus, I'll rewrite it. It says prove convergence. We'll just say it converges. I'm not going to take the time to prove that right now. I'm just going to say this is a convergence series approximated to 5 decimal places. This would be a calculator problem. So what you do is you just add up the terms. You find the other thing we might ask is how many terms. So I might say how many terms to get within 0.001 of the actual sum. So what you do is you just start finding points. I'm going to take out my calculator right now, and I'm just going to do this. Oops. I'm going to go 1 divided by, let's just say n. I'm just going to guess and check right now. Or actually, no, I'm not even going to guess and check. Whoops, that's a factorial. Yeah, I'm going to guess and check because it's a hard problem to solve. Algebraic. Normally, you would just do this. 1 over 2n minus 1 factorial is less than 0.001. And then you algebraically solve that. That's kind of a pain with this one because of the factorial. So you get 2n minus 1 factorial is equal to, 1 over 0.001. And you could either guess and check on your calculator, or if it's just a simple algebra equation, sometimes you might get something like just 2n plus 1, is less than whatever, 100, whatever, I'm just making up numbers, then you can solve that. So the idea there is that if you add up the first n terms, the next term, the n plus first term, is how far the maximum difference you can be from the actual sum. And we'll go over a lot of those in class and kind of practice. Hopefully that'll help you a little bit.